Have you ever thought that a weapon the length of your arm can hit a target accurately beyond half a mile at minus 40 degrees Fahrenheit and plus 140 degrees Fahrenheit? Metal expands in heat, contracts in cold. A system with zero tolerances should either seize up or rattle loose, and in both cases, miss. But it does not, and the reason is not where you would think. Here is one number, 0.000065 inches per inch per degree Fahrenheit. That is the thermal expansion coefficient of steel. Sounds negligible, means nothing on its own. So picture a rifle barrel 20 inches long, heated from minus 40 to plus 140 degrees Fahrenheit, 180 degrees of difference. It grows by approximately 0.023 inches. Less than a quarter of a millimeter. The width of 5 human hairs laid side by side seems trivial, but a sniper rifle like the Accuracy International AXMC and 338 Lapua Magnum has a design accuracy of less than 1 minute of angle, meaning at 1,000 yards, every shot must land within a circle less than 10 inches in diameter, under ideal conditions with match ammunition closer to 5 inches. But if temperature shifts the geometry of the barrel's attachment to the stock, even by those same tiny fractions, your grouping at 1,000 yards doubles in size. Mission failed. Target walks away. So yes, a fraction of an inch matters. Most people assume the solution is simple. Make the looser tolerances. Part sits a little freer, nothing seizes up or binds. At first glance, this sounds reasonable, and it's partially true for certain mechanisms. But here is the problem. Looser tolerances mean added play. Play in the bolt group means that with every shot, parts settle into slightly different positions. And if part positions vary, so does the bullet's exit point from the barrel, even by thousandths of an inch. At 800 yards, those thousandths become inches. Looser tolerances do not solve the problem, they just swap one source of error for another. The real answer is not fighting thermal expansion. Everything comes down to the principle of matched expansion. If all components in a system expand predictably and symmetrically, the system maintains its geometry even as the material physically moves. Precision is not stillness, it is predictable movement. If every part moves in a known, symmetrical, repeatable way, the system holds its geometry, even as dimensions physically change. That single idea is the foundation of all sniper engineering, and we are about to walk through 4 systems, each one proof of it. But the core question remains, if metal moves with every temperature change, how can a system stay precise at all? The simplest answer that comes to mind is to choose materials that expand less. Such alloys exist. Invar is an iron-nickel alloy with a thermal expansion coefficient 10 times lower than ordinary steel. Problem solved? Not quite. Invar is heavy, expensive, and difficult to machine. A rifle is not a laboratory instrument. It gets dropped, hauled in dirty vehicles, laid in sand. Materials have to be practical, so material selection is only the first layer. There is a deeper reason why material alone cannot solve the problem. A rifle is not one material. It is a system of dozens of different alloys, polymers, and coatings, each expanding at its own rate. The barrel is steel, the receiver is also steel, but a different composition. The stock is an aluminum chassis with polymer panels. Scope rings are one alloy, the scope body is another. Even if you found the perfect material for one component, the rest of the system still moves on its own terms. Those movements pull in different directions. One assembly expands faster, another slower. Tension develops between them. Tension at a connection point means a microscopic geometric shift. Engineers call this differential thermal expansion. Think of a bridge. Every bridge is designed with expansion joints precisely because the steel in it moves. A rifle operates on the same principle in miniature. Every system moves with temperature change. The engineer's job is not to stop the movement, it is to make the movement predictable and symmetrical. When two materials with different coefficients are rigidly connected, temperature change causes one to deform, or to push the other out of position. This is not theory, it is measurable. It is exactly why no single right material can solve the problem. The solution isn't in the material, it's in how the parts connect, and this is where engineers made a move most people don't see coming. The real approach is constructive compensation, and this is where it gets interesting. The barrel in a sniper rifle doesn't attach to the stock rigidly along its full length. It contacts the stock at only one point near the chamber. The rest of the barrel hangs free. This is called a free-floating barrel. The concept has existed since the 1950s, but its physical logic still isn't obvious to most shooters. Why free float? Because if the barrel contacts the stock along its full length, any deformation of the stock from temperature, humidity, or even the shooter's grip pressure transfers directly to the barrel and changes its vibration point. A free-floating barrel vibrates independently, and that vibration is predictable. Yes, the barrel vibrates with every shot. That's not a flaw. That's physics. The bullet exits the barrel at a specific phase of that vibration, and if the phase is consistent, the exit point is consistent. But here's where it gets genuinely interesting. The free-floating barrel solves the stock problem, but there's another system that also moves with every shot, one most people never think about. The sight line, specifically how the scope is mounted. A modern sniper scope, like the Schmidt and Bender 5-25 by 56 PM2 weighs over 2 pounds and mounts to a Picatinny rail through 2 rings. The tolerances between the scope body and the ring metal are minimal. The scope cannot shift under recoil, but those same zero tolerances mean that when temperature changes, the aluminum alloy scope body and the steel rings expand differently. Aluminum's expansion coefficient is 0.0000131 inches per inch per degree Fahrenheit. Steel's is 0.000065, roughly double. The scope body wants to expand more than the rings allow. Stress develops. That stress, if uncompensated, microscopically shifts the optical axis relative to mechanical zero. Two solutions exist. First, rings made from the same aluminum alloy as the scope body. They expand identically, so no stress develops. Second, torque-specified mounting with a calculated clamping force. Rings are tight enough to hold the scope under recoil, but at thermal extremes they can slip fractionally without shifting the axis. This is not intuitive, it is engineered. During operations in Afghanistan, this exact problem, mismatched materials in rings and scope body, produced point-of-impact shifts of 6 to 8 inches at 600 yards between early morning and midday. Documented, solved by switching to aluminum rings. Most engineers would stop there, but there is one more level, and it has nothing to do with metal or optics. It is in the cartridge itself. Powder does not burn the same way at different temperatures. This is not intuitive. You open the bolt, seat the round, it looks identical, but the chemistry inside the case is already different. At plus 140 degrees Fahrenheit, powder gases form faster. Pressure in the chamber rises more steeply. The bullet exits the barrel at a higher muzzle velocity, roughly 100 to 165 feet per second, faster than the standard at 68 degrees Fahrenheit. That sounds small, but at 875 yards, that velocity difference shifts the point of impact roughly 10 to 14 inches vertically. You aimed for center mass and hit the stomach, or missed entirely. At minus 40 degrees Fahrenheit, the reverse is true. Gases form more slowly and pressure builds gradually. The bullet travels slower, wind deflects it more, and gravity acts for longer. Same target, same distance, and the shift is again 8 to 12 inches, but in the opposite direction. This is a problem metal cannot solve. No mounting system, no stock material helps when the propellant charge itself delivers an unstable impulse. The industry responded 2 ways. First, temperature-stable powders. Companies like Hodgdon and Vikhtavori developed powder series, Hodgdon Extreme and Vikhtavori N560 for example, with minimal temperature sensitivity coefficients. The velocity spread from minus 25 to plus 125 degrees Fahrenheit for these powders is under 80 feet per second, versus the 165 to 260 feet per second, typical of standard powders. This isn't marketing, it's measurable with a chronograph. Second, ballistic tables with temperature correction. Every serious sniper unit tracks not just range and wind, but range plus wind, plus temperature, plus elevation above sea level. With modern ballistic calculators, applied ballistics, or Horn 84 DOF, you enter air temperature and ammunition temperature separately. If a magazine sat in a cold vehicle and you then chambered a round, the cartridge is at 10 degrees Fahrenheit, while the air is already 40. These are different inputs. The calculator accounts for both. SAS and Delta Force snipers in the field keep cartridges close to their body in cold conditions. And here's the honest part. That's not a written protocol. It's a human decision in conditions where no engineering gives a complete answer. Cartridge temperature is the one variable in this entire system that remains dependent on the person, not the calculation. It isn't superstition, it's thermodynamics. The temperature of the round at the moment of firing should be as close as possible to the temperature at which the rifle was zeroed. A 15-degree difference in the cartridge itself produces more error than a 15-degree difference in the air. This is where all the threads converge: metal geometry, optical stability, lubrication, and now the chemistry of the shot itself. The precision of a sniper system is not a property of any single component. It's an equilibrium between four systems, each of which must behave predictably in conditions where most mechanisms simply degrade. The whole system, metal, optics, lubricant, powder, isn't designed for a perfect shooting range. It's designed for the real world, where temperature swings, where hands shake from cold, where the decision has to be made in a second. 4 systems, 4 failure points, each solved differently. The cost of failure is the first shot that doesn't connect, the mission that ends a second before it should have, the shooter who no longer trusts his weapon, and that's the worst thing that can happen before the trigger is pulled. You now know more about a rifle than most people who have held one, about what happens inside the system when temperature drops 180 degrees Fahrenheit and every material starts doing its own thing. This is engineering that doesn't announce itself. It simply works, which is exactly why nobody notices it. The next time you see a sniper in a news report, you won't look at the rifle as a piece of metal with glass on top. You'll know that behind every joint is a calculation, behind every shot in extreme conditions, decades of quiet work by people whose names will never appear in the headlines.